Welcome back students to the discussion on different burning stages within the stars, which are responsible for not only the energy production, but also for the synthesis of different elements. Okay. In the previous lecture, what exactly we have discussed with I will have a quick review and then I will continue today's discussion. Okay. So, in the previous lecture I have discussed PP1, PP2 and PP3 chain reactions, and we have seen the most loss of the energy is within the PP3 chain because of the escape of the neutrinos, and also have discussed carbon nitrogen cycle, which are mainly happening within the population 1 stars, where heavier elements are present in enough heavier elements like carbon and nitrogen are present. And in today's lecture I will continue how these CN cycles are happening in different ways and how more cycles are happening within the stars, which are responsible for different types of chemical elements. And I will also spend some time on the shell model and the energetics of gamma decay, which are very important to understand the different aspects of nuclear astrophysics. Okay. So, in CNO bicycle, please remember earlier the carbon 12 led to the production of nitrogen 13 via P gamma, and this nitrogen 13 gave rise to carbon 13 via positron decay, and this carbon 13 based on proton gamma reaction, it has given rise to the production of nitrogen 14, and nitrogen 14 via again P gamma, it has produced oxygen 15, and oxygen 15 via positron decay has produced nitrogen 15, and this nitrogen 15 via P alpha reaction has produced carbon 12, and there we have said that carbon 12 act as a catalyst and 4 protons are converted into helium 4. However, we have ignored a process in this cycle, that is nitrogen 14 instead of undergoing reaction via P gamma, coming back to this cycle, nitrogen 15 instead of P alpha, it can also undergo P gamma reaction. Okay. Nitrogen 15 can undergo reaction with proton to produce oxygen 16. Okay. And this oxygen 16 undergoes reaction P gamma to produce F17. See, in all these reactions, because of the abundant nature of the protons, they are able to induce so many charged particle reactions. Okay. And this fluorine 17 is unstable and they undergo positron decay. See, as the mass number is increasing, the circle size is also increasing. Just for the sake of convenience, I am using different sizes of circles for different nuclei. Okay. And this oxygen 17 undergoes reaction with proton, producing alpha particle and giving rise to nitrogen 14. So, we can say that this is cycle 1 and this is cycle 2 in CNO. In plus 2, you might have heard PP chain and CNO cycle, they are responsible for the energy production in the stars and sun. So, in terms of energy production, it is a PP chains, but whereas in terms of more number of synthesis of elements, it is the CNO cycle which is playing important role. Okay. So, let us see some more features of this CNO cycle. As I said earlier in the previous slide, we have neglected the reaction proton plus 15 N15. Okay. Now, after including this, which can always happen, okay, within the stars, we have 2 cycles. Okay. However, the importance of this second cycle related to the first cycle, that is CN cycle, is governed by the ratio of S factor at 0 energy. Okay. You know how this S as function of at 0 energy can be obtained is basically at available energies you measure the S factors and extrapolate to the 0 energy. That is what is important parameter in the nuclear astrophysics. Now, for these 2 reactions, if we see Q value is 12.126 okay, for the first reaction, and if we see the S at 0 for these 2 reactions, the ratio is 1000:1. Okay. So, proton plus nitrogen 15 okay, giving rise to carbon 12 plus alpha is more probable than P gamma reaction. So, P alpha is more probable compared to P gamma. Nevertheless, in the presence of large number of nitrogen 15 nuclei, it is also possible 1 in 1000 can be through P gamma. Okay? So, this is what we need to understand, and the second cycle as expected contributes very little to the total energy production. Now, let us see some additional cycles within the CNO cycle. Okay. Carbon 12 as usual via P gamma, let me use the same color for the sake of convenience. Okay. And nitrogen 13 gives rise to carbon 13 via positron decay. Okay. And by P gamma it gives rise to nitrogen 14, and nitrogen 14 by undergoing reaction with proton it gives rise to oxygen 15, and oxygen 15 by undergoing positron decay it gives nitrogen 14, and this via reaction P alpha, not P gamma, gives rise to carbon 12, and this is via P gamma. So, I am drawing the same cycle when compared to the previous one. Okay. And via P gamma it gives fluorine 17, and fluorine 17 by undergoing positron decay it is oxygen 17. Now, this oxygen 17, as I said earlier, P alpha it undergoes reaction with that, and you can see that nitrogen 14 is again produced. That is what we have seen in the previous slide. Now, there is also possibility that oxygen 17 can undergo again reaction via P gamma to produce fluorine 18, which further produces via positron decay oxygen 18 nucleus, and this oxygen 18 nucleus can undergo reaction with proton emitting alpha particle, okay, and giving rise to nitrogen 15. All right. Not only that, this oxygen 16 can also produce via P alpha reaction fluorine 19. Okay. Not only that, even oxygen 18 also can produce fluorine 19 via P gamma reaction, and by forming the neon 20, this cycle will end. This cycle will end. Okay. So, we can see that overall we can see that cycle 1, cycle 2, cycle 3, and we can say that this is the cycle 4. All right. So, these 4 different cycles can happen within the CNO cycle depending on the availability of different nuclei. Remember, CNO cycles mainly they are important considering the synthesis of elements, not the energy produced from the stars. So, at what stage which nucleus undergoes P alpha and P gamma undergoes positron decay, it has to be understood by seeing the mass numbers, and to some extent you need to remember them. Okay. But this CNO cycles gives an overall idea what kind of isotopes of different elements are produced. Okay. Now, let us continue the discussion. If we consider the oxygen 18 when it is reacting with the proton, okay, and when it is reacting with the proton it can emit either nitrogen 15 or it can emit fluorine 19. Okay. Now, this ratio of the reaction rates as a function of T, if you see, that is quite interesting. Okay. The ratio of the reaction rates, if you see, okay, see the temperature on x axis, and reaction rate when you consider oxygen 18 P alpha, okay, reaction rate of same oxygen 18 not via P alpha, but via P gamma. You can see this from 10 to the power of 7 to 10 to the power of 10 if you see. So, say 10 to the power of 4, say 10 to the power of 2, 10 to the power of 3, then it varies like this. Okay. What does it mean? At T9 less than 0.02 and greater than 0.7 at T9 values, the hydrogen burning takes place entirely through P alpha reaction, entirely through P alpha reaction. So, at what temperature range, by what kind of reaction oxygen 18 is undergoing destruction mechanism. That will be clear if you take the ratios of two different reactions in which entrance channel is same, but exit channel is different. And this diagram shows us that under which temperature range which reaction is dominant. Okay. Now, if we consider the another nucleus, that is fluorine 19, this proceeds through fluorine 19 plus proton, giving rise to alpha plus oxygen 16. All right. Now, because of this CNO cycle catalytic material, they remain in the cycle, which leads to the occurrence of fourth branch in CNO hydrogen burning. However, if fluorine 19 does not participate in P alpha, but it participates in P gamma, then the catalytic material will be lost through this reaction, forming the neon 20. So, with this CNO cycle is ended, forming the neon 20, and this neon 20 initiates some other cycles. Okay. Now, this neon 20 forms basis for further hydrogen burning through neon sodium cycle, neon sodium cycle, which is interesting to understand how different elements are formed. Okay. And to what extent fluorine 19 returns or is lost, and location of the site of fluorine 19 nucleosynthesis, it is basically depending on the more experiments are needed to be done for proton energies less than 250 keV, less than 250 keV. So, let me quickly show you in a different way these four branches of the CNO cycle. Okay. CNO1, CNO2. Okay. So, initially carbon 12 goes to nitrogen 13, it comes to the nitrogen 13, carbon 13, then goes to nitrogen 14. So, in terms of mass numbers and proton number and neutron number, this diagrams helps us, CNO3 and CNO4. Okay. So, this is some representation of four branches in the CNO cycle, which I have drawn in the previous slides. And here the stable nucleates are shown as shaded squares, and each reaction in CNO branches involves the conversion of 4 protons to 1 helium 4 nucleus. Okay. And if you see the hydrogen burning at high temperature, say 10 to the power of 9 kelvins or more, and at higher density like supermassive stars like nova and supernova, and CNO cycle operate at in a rapid way. Okay. That is in within seconds, and this beta unstable nuclei nitrogen 13, fluorine 17, fluorine 18 and neon 19. What exactly I am trying to say in this slide? Whenever the situation is in such a way that temperature is very high, density is very high, and you have seen many nuclei in this PP chain and CNO cycle, that they are reacting with, they are undergoing decay if they are unstable. I repeat, a nucleus which is unstable, they are undergoing positron decay to give a stable nucleus, right. This may not happen always. If these same unstable nuclei are in the environment where temperature is very high and high concentration is there, before it undergoes positron decay, it can always react with proton, leading to another reaction. Okay. So, that is what I am trying to convey in this slide. See a beautiful diagram in this slide. Okay. So, when CNO cycle come across the very high temperature, it operates at a rapid rate, and whatever unstable nuclei are there, nitrogen 13, fluorine 17, 18 and neon 19, they react with protons before decaying. So, you can expect a many cycled monster in the stars. Where exactly it is denoted, my dear? You see here nitrogen 13, earlier it was undergoing positron decay, right. Now, if enough number of enough protons are available, which is always the case, but at high temperature and high density, this can undergo proton gamma reaction, that is the case. Okay. And oxygen 14 will give rise to nitrogen 14. So, this is where you can see nitrogen 13, and where is fluorine 17? This is where. Okay. This fluorine 17 can react with the proton and give rise to neon 18 and produces fluorine 18, and once again oxygen 15. And where is F18? This is the one. F18 earlier I have discussed, it is produced because of another reason. Now, because if it is reacting with the proton, it goes to another cycle, okay, where this dotted circle is shown to you. Okay. And if it is not going to oxygen 16 via positron via P alpha, okay, it can always also goes to oxygen 18. Now, you can also see here neon 19. Neon 19 also can lead to the production of neon 20. How? By reacting with proton, it can produce sodium 20, which can undergo positron decay to produce neon 20. So, you have this P gamma, P alpha and positron decay possible at high temperature. That is what I am trying to convey in this slide. Okay. Now, in this CNO cycle, when it is ending with neon, okay, this fluorine 19, if you remember, this is producing basically neon 20 via P gamma, and this neon 20 via P gamma can produce sodium 21, and this can undergo positron decay to produce neon 21, and it can undergo P gamma reaction, okay, to produce sodium 22, and this can undergo positron decay to give neon 22, and neon 22 can undergo proton gamma reaction to produce sodium 23, and this sodium 23 can undergo P alpha reaction to produce neon 20. This is called as neon sodium cycle. You see, so many nuclear reactions are happening within the cycles. Now, this sodium 23 can also undergo reaction, that is P gamma, to produce 24 Mg, which can produce aluminum 25 via P gamma, which can undergo positron decay. It is unstable, it can produce Mg 25, and this can give P gamma to produce 26 aluminum. This can produce Mg 26 via positron decay, and Mg 26 can undergo P gamma reaction, okay, to produce 27 aluminum, and this 27 aluminum can undergo P alpha reaction to produce 24 Mg, and this cycle is called as Mg-Al cycle, starting with Mg and ending with Al. Now, this Al 26 can also undergo P gamma reaction. There is another possibility. See, there are so many possibilities to produce silicon 27, which can undergo positron decay to produce aluminum 27, and this aluminum 27, instead of undergoing P alpha, it can also undergo a reaction, that is P gamma, to produce 28 silicon. Okay, 28 silicon. So, what this diagram tries to tell us, depending on the availability of nuclei and the probability of undergoing reaction via P gamma or P alpha, different cycles can occur within the stars. And in this neon sodium and magnesium aluminum cycle, there is a situation when it is coming out of the cycle by forming silicon 28, and then we have silicon burning, and then different burning stages up to iron elements, and beyond iron we will see it is because of the neutron induced reactions. Here you see nowhere you have come across the neutron induced reactions. It is because of the charged particle induced reactions and the positron decays, different elements are formed. Okay. So, this neon sodium and Mg-Al cycle, they are not important for energy production like CNO cycle because of the very high Coulomb barrier, but for the synthesis of elements between neon 20 and aluminum 27. And interestingly, in these cycles you can see neon 22 and aluminum 26. Already I have discussed in the initial part of the lectures the discovery of aluminum 26. They are found in meteorites. So, this is how these elements are important, which are part of the CNO cycles. And abundance ratios of any pair can be found from the ratio of the relevant reaction rates. Okay. So, up to this I have discussed PP chain, CNO cycles and additional cycles. Okay. And as I have said in the initial part of the lecture, other than PP chain and CNO cycles, there are two topics which looks to be different from the ongoing discussion, but I thought it makes sense to throw some light on these two topics, so that the concepts will be useful to you whenever gamma decay is discussed. Okay. Come, let me quickly give you some insight about the shell model. Hope it is being taught to you in your BSc or MSc. So, that is why I will not take much time, I will just to discuss the salient features. So, in +2 you might have been taught liquid drop model, which could not explain the magic numbers and the existence of different energy states, right. So, that is where the advantage of shell model is there, which predicts the properties of not only closed filled shells, but also partially filled shells. Okay? And this shell model, how it is important in this nuclear astrophysics course? Many a times you need to calculate the gamma ray transition strengths. Why gamma ray transition strengths are important? Up to this I have shown you many reactions like P alpha, P gamma, all those things, right. Many a times you have come across P gamma reactions. So, once the nucleus is reacting with the proton, the compound nucleus is formed in the excited state, and during de-excitation gammas are emitted. So, many times when you try to model the stars while developing the stellar models, it is important to have the value of this gamma ray transition strength and spectroscopic factors and weak interaction matrix elements. Whenever proton is involved, normally you come across weak interactions. There this shell model plays important role, and this helps us to understand the spin and parity of the nuclear state. What is parity? It is related to the symmetry when wave function is reversed in order. Okay? And compared to atomic shell model, already you might be aware of this atomic shell model. More or less they are same, but there is some difference also because of the lack of precise nuclear potential. We are aware of precise atomic potential, but it is not the case with the nuclear potential. It is lacking, we do not have the proper information. And here we have two types of particles like neutron and protons, whereas in the atomic shell model you have only electrons. And there is no heavy center of force for nucleons. Like in the case of atom, there is a heavy center of force in the form of nucleus. That is how atomic shell model can be understood, but nuclear shell model cannot be understood in the same way. Nevertheless, by assuming simple harmonic potential, we can get some idea, and by using a potential like Woods-Saxion potential, I will not go into the details, you can see in any textbook, which tells us there is a strong coupling between the spin angular momentum and orbital angular momentum. Okay? And solving the Schrodinger equation for this harmonic or Woods-Saxion potential, you can see that single particle states are characterized by principal quantum number, orbital quantum number, and total quantum total angular momentum quantum number. And you know very well that each energy level has this total angular momentum, and at max 2j plus 1 nucleons, either neutrons or protons, can be occupied, and normally we use this symbol -1 to the power of L for the parity. If L is equal to odd, L is equal to 0, even, then we say even parity, and L is equal to odd, we say odd parity. That means the wave function does not change. Okay? Now, this is the shell model essence. Please look into any textbook where you can see for different L values the splitting of the energy levels is taking place. Okay? And how the positive parity or negative parity is used based on -1 to the power of L. You can see, okay, L is equal to 1, so -1 to the power of 1, it is odd, so parity is negative. And you see L is equal to 4, -1 to the power of 4, so it is positive parity. Alright. So, like this one can find out the parity and the J values and the total number of nucleons occupied. Okay. And the stable labels are represented by this symbol NLJ, where N denotes the order of occurrence of given value, and L 0, 1, 2, 3, 4 correspond to these different orbitals like atomic orbital model. And as I said earlier, each state can occupy 2j plus 1 neutrons and 2j plus 1 protons, corresponding to 2 into 2j plus 1 distinct configurations of identical nucleons, so that Pauli exclusion principle can be satisfied. Okay? So, this is the main essence of the shell model, which tells us whether the spin and parity is plus or minus and some fraction. Why these values are important? Because according to the selection rule, the emission of gamma depends on this spin and parity. So, that is the reason I have spent some time in giving you the information of spins and parities based on shell model. Now, let me move on to the gamma decay, which is one of the important process in nuclear astrophysics. Okay? Now, in the gamma decay, we know that each nuclear state has a specific excitation energy, and it is possible to populate the energy levels by say a reaction like capture or decay or Coulomb excitation or scattering process. So, using various means one can populate the nuclear levels, and most important transition from higher to lower is via gamma decay, though other processes are also possible like internal conversion and internal pair formation, where the energy difference is converted into positron and electron if the energy difference is greater than 1.02 MeV. But this is the most preferred transition, and we can see that schematic of a gamma source decay scheme. If you see a simple source like gamma, okay, let me draw here for you so that you can understand how the simple decay scheme looks like. The widely used gamma source in the laboratory is cesium-137. This is unstable. Okay, it decays to the excited state of barium. Okay, excited state of barium-137, and this excitation leads to the emission of gamma ray during de-excitation, barium-137, and this is via beta minus, whose endpoint energy is up to 0.5 MeV, like that. Rarely this can directly go to the ground state, this also via beta minus. So, this is a schematic of a gamma source decay scheme, and in due course I will explain how a gamma spectrum looks like. Okay? This is not of our interest at this stage. Now, remember this gamma emission, for when we test the detectors in the laboratory, they always preceded by the beta decay. Okay? And the difference between X-rays and gamma rays is basically the origin, though basically both are part of electromagnetic radiation. Okay? Gamma rays are because of the nuclear processes, whereas X-rays are emitted because of the atomic processes, rearrangement of the electrons in the shells. Okay? Continuing the discussion on gamma decay. If you see the energetics of the gamma decay, remember once gamma is emitted, the nucleus will undergo recoil. Okay? So, considering this in mind, the energy of the gamma ray is energy of the initial state and energy of the final state. Normally EF can be ground state, okay, and the recoil nucleus. And you know, the kinetic energy of this recoil nucleus is normally very, very less. So, that energy of the gamma can be considered as the difference in the energies of two levels which are involved in the transition. And these two states, they have different angular momentum and parity, and the transition from this initial to final state is related to the emission of photon. That is the reason it should connect to the two states and conserve the parity and angular momentum. You are aware of conservation of energy and momentum when collision happens. In the same way, when gamma is emitted from the excited nucleus, the conservation of parity and angular momentum also plays very important role. This is the essence we need to understand. Okay? Just I will spend couple of minutes in this lecture, so that we can understand more important features of gamma decay. You see, this is the angular momentum in the integral multiple of h cross, initial and final state. They are the angular momentums of two states involved in the transition, and the change in the intrinsic angular momentum is nothing but delta h cross. So, the emitted photon, that means gamma ray, can be classified according to the angular momentum, that is what is the amount carried out by the photon, where L is equal to 1, 2, 3, 4 you can consider, and according to the parity. And what are the possible values of L, my dear? They range between the delta H cross, okay, IF minus II and IF plus II H cross. So, this relation you know very well. And what is the nature of this gamma ray? It could be dipole, it can be quadrupole, it can be octopole. Okay? How to decide it? That can be decided by an expression called as 2 to the power of L. I am not going into the details, you can refer any basic nuclear textbook. The derivation will be, and theory behind this 2 to the power of L concept will be clear to you. But here I am interested to tell you the nature of the gamma ray emitted in this transition. It is 2 to the power of L. If it is L is equal to 1, it is 2, L is equal to 2, that is quadrupole, L is equal to 1, dipole, like that you can continue. And if it is L equal to 3, it is basically 2 to the power of 3 is 8. So, we can say that it is a octopole in nature, this electromagnetic radiation, alright. And this is regarding angular momentum. What about parity? The change in parity depends on either the distribution of matter is changed, that means nucleons, how the nucleons, that means protons and neutrons are arranged, or charge is changed during the transition. So, the change in the distribution of matter and charge will decide whether it is electric or magnetic in nature. So, keeping this in mind, one can say if it is electric in nature, if it is minus 1 to the power of L, magnetic in nature can be understood by taking minus 1 to the power of L plus 1. The reasons I am not explaining in today's lecture, you can go through another textbook. Okay. So, now let me give you a brief idea, some overview of these types and depending on polarity. If L is equal to 1, it is electric in nature, minus 1 to the power of L. Okay. So, it is E1 and the nature is electric dipole. So, there is a change in parity, yes, because minus 1 to the power of L is odd. Now, the same way, if L is equal to 1, okay, minus 1 to the power of L plus 1 for magnetic, right. So, the change in parity is not possible and the same dipole is there, okay, and for magnetic it is M1, but parity there is no change. Now, if it is L is equal to 2, minus 1 to the power of L, okay, so it is even. So, parity is there is no change and electrical in nature and L is equal to corresponds to quadrupole. Similarly, you can write down magnetic quadrupole and magnetic octopole and whether there is a change in parity or not. Let me take one example for better understanding. Let me take a nucleus sodium 23. It is undergoing transition from a state which is characterized by 7/2 plus to 3/2 plus. All right. There is a transition of 23 sodium where this is denoted by 7/2 plus and this is denoted by 3/2 plus, where this is the total angular momentum called as also spin and plus is a parity. Now, what are the possible values? Is there any change in the parity? Is there any change in the parity? You can clearly see that there is no change in the parity because it is a plus, it is plus. There is no change in the parity. This is clear from here. What are the possible L values? You can see the difference and sum of the angular momentum, that is total angular momentum is spin 7/2, 3/2. This gives rise to 7/2 minus 3/2 is, you can see 2, 7/2 plus 3/2 gives rise to 5. So, L can assume 2, 3, 4 and 5. Now, based on these L values, you can write down the electric or magnetic nature. For example, if L is equal to 2, okay, it is even. So, there is no change in the parity anyway, plus to plus. So, there is no change in the parity and the type is E2, because when there is no change in the parity and if L is equal to 2, it is electrical nature, and if L is equal to 3, it is odd, then L is 3, magnetic in nature, and again when L is equal to even, electric in nature, and when L is equal to 5, it is magnetic in nature. Okay. So, to summarize, in today's lecture, I have discussed additional cycles possible within the stars based on carbon and nitrogen and continued up to neon sodium and magnesium aluminum, and then I have discussed some salient features of the shell model which tells us the values of spin and parity of the states. And once I have shown you how spins and parity are decided based on some conditions like minus 1 to the power of L, minus 1 to the power of L plus 1, one can say whether there is a change in the parity or not and whether the emitted gamma ray is a dipole, quadrupole or octopole, and whether it is electric in nature or magnetic in nature. So, these topics will be useful for us to understand the transition in different nuclei when they are in excited state. I hope you were able to follow what exactly I am trying to convey in these lectures. So, continuing these different burning stages, I will take up some advanced burning stages in the next lecture. Okay? Thank you so much for your attention. See you.